This month's long answer question focus is on questions about ionization energy. So here's our question. We're given the first 5 ionization energies of 2 elements, magnesium and aluminium, in a table. And then we're asked to refer to the electron configurations of the element and use them to explain the differences between the first ionization energies and the second ionization energies. So although this is a 6-mark question, what's actually happening, you can probably see, is that you're going to be getting 3 marks for the first part of the question and 3 marks for the second part of the question. It's not always the case that they're evenly split like that, but it is super common for longer questions to actually appear as 2 different bullet points, or even sometimes 3. So it makes it a lot easier to structure our answer. Now, when we're answering questions about ionization energies, there are always some really clear ideas that we can link to ionization energy, whether it's first, second, third, whatever, or successive for an element. So we're always talking about the energy required to remove an electron, and that energy simply depends on how strongly attracted it is to the nucleus of the atom or the ion that we're removing it from. So attraction is the thing that we want to focus on. Now, that's going to depend on nuclear charge, because obviously the more protons we have in the nucleus, the more strongly attracted an electron could be. It's going to depend very heavily on the distance from the nucleus, because all forces of attraction like this depend on how far away the 2 things that are attracting each other are. And it could also depend on shielding. Now, we'll talk about when we use shielding in a moment from inner shells, and also there might be something about repulsion from paired electrons. Now, shielding only comes up when we are talking about different shells. Not different subshells, not different orbitals, literally different shells. So we're talking about things that are in different rows of the periodic table. Magnesium and aluminium are both on the same row of the periodic table, so we're not talking about that here. So no mention of shielding whatsoever. Repulsion from paired electrons is a really specific case, and we only ever really see it. We see that in the middle of the P block or the D block. And that's a sort of case, for example, there are 3 p orbitals. They can each hold 2 electrons. So for example, nitrogen has 3 p electrons, oxygen has 4, which means that the one in oxygen has to share an orbital, and there's a little bit of extra repulsion. That is not the case for magnesium and aluminium, so we're not going to talk about that either. And in fact, one thing to point out that I get students saying over and over again, do not talk about extra electrons as being a reason for anything, okay? Because it's only these 4. These are the only 4 we should talk about. So let's look at the first ionization energy difference. First of all, that's the more common question that we're going to get answered. So the first ionization energies of the 2 elements, what can we see? We can see that aluminium first ionization energy is lower than magnesium. So we also need to refer to electron configurations. So the first thing I'd be doing in this question is writing those electron configurations out. Now they're both in the same shell, so it's not going to be enough to just write 282 and 283, because that isn't going to explain anything. If the electrons are in the same shell, then you would think that they're just going to be the same distance from the nucleus. So aluminium is 1s2, 2s2, 2p6, 3s2, 3p1, and magnesium has 1 less electron. So all of this bit will be the same, we've filled, and its outer electron is here. So this is what we want to focus on, is the outer electron. Again, we don't want to talk about filled or unfilled here either. That's not ever really anything. Lots of people sort of focus on full things and say, oh, magnesium's got full subshell, so it must be that. It's not that. So what we're saying is that aluminium's outer electron, do talk about outer, keep putting that word outer in, especially when you're doing first ionization energy, is in 3p, mg's is in 3s orbital. Being really specific, I'm not just saying s and p because they might be in completely different energy levels, so I'm being specific about that. We can also say that the 3p subshell is higher in energy. Now, you could say further from the nucleus. They actually mean the same thing. It sort of really depends whether you're thinking about like actual distance, which is actually a bit of a weird thing to think about with atoms because they're so small, or if you think of a shell as an energy level, and the further away it is from the thing it's being attracted to, then the higher in energy it will be. If you imagine like it's like being higher up a hill than the 3s orbital. So it's higher in energy and therefore requires less energy to remove. If something's already higher up a hill, it's easier to push it to the top. So always link it to the actual difference that we have. And the reason it requires less energy is because the attraction between the outer electron, keep saying outer, and the nucleus is less for aluminium. Again, I'm being complicated. Every time we're comparing things, let's make sure we say, if we ever say less or more, make sure we're saying what is less. So in this case, aluminium is less attraction. Also, when we're talking about attraction, let's use the word attraction. Let's not use pull or any other sort of weird word. And let's also say that what is it being attracted? So attraction between outer electron and nucleus. Don't get lazy and just say it's less attracted, because that doesn't really mean anything. Okay, that's the first half. We've got 3 marks. So the marks there are for stating the electron configurations, the full electron configurations. Then talking about 3p subshell being higher in energy, and then relating it to the lower attraction between the outer electron and the nucleus. Okay, we now have the second part, which is talk about second ionization energies. So remember that second ionization energy is taking a positive, a 1+ ion, and then removing the next electron in to form a 2+ ion. So what we can do is we can look at what we start with. So in both cases, 1s2, 2s2, none of this has changed, 2p6. And then for aluminium, it's just going to be 3s2 because we've lost that 3p1 electron in the first ionization energy. And for Mg+, it's going to be 1 electron less than that, so it'd be 3s1. So what we can see now is that the electron is removed from the same orbital. Now we do have a sort of paired unpaired thing, and you might be thinking, oh look, there's a full orbital and then there's a half-filled orbital. Now I could look at that, and if I did, what would I predict? I would predict that the filled orbital would be repelling each other and therefore would be easier to remove. That's not what the table's telling me. The table is telling me it's harder to remove the second electron from aluminium than it is from magnesium. Now actually, therefore, it's not about electron pairing. Because we've got the same orbital, that means it's not about distance, and that means it's also not about shielding. And so the only thing we've got left after we've sort of taken into account how far away the electron is and what's in between and whether it's being repelled by anything else is the nucleus. And for some reason, it's a bit that everyone forgets. there's a difference in the nucleus. Aluminium is one element further over in the periodic table. So aluminium has one more proton. We could either just say it has one more proton, or we could just say it has a greater nuclear charge. It had a greater nuclear charge in the last question as well, but that was cancelled out by the effect of the 3p being further away than the 3s, in the same way that it would be cancelled out if you went into a whole new shell as well. But this time it's the nucleus. So anytime you have an increase in ionization energy between two elements or anywhere else, then it is about nuclear charge, always explained by more attraction. It's the only thing that can really give you more attraction. So aluminium, greater nuclear charge, and therefore greater attraction, just like we did with the last one, between the electron removed. I'm not actually going to call it the outer electron, just because that might be confused a little bit, because we're now on the second ionization energy, and the nucleus. And so we need more energy to remove. And again, I feel like I haven't said aluminium for a while, so I'm going to put it in from aluminium so it's super clear. That's what you've got to do in all of these questions. Make sure you're comparing what stays the same, so same orbital, or in the previous case the same row, the same shell. What's different? In this case nuclear charge, in the other case different subshell, and therefore what effect that has on the attraction between the nucleus and the electron that you're removing.